Hi, my name is Davis Chamorro. Today I'll be giving you a brief look into the material science of spider silk. Spider silk is produced by all spiders and is used for hunting, webs, drag lines, parachuting, shelters, egg sacs, and even mating. Spider silk, specifically drag line spider silk, is special because it is tougher by weight than steel, roughly 5 times tougher than steel of the same diameter. Toughness is a combination of tensile strength, the resistance to breaking under tension, and ductility, material stretchiness under tensile stress. Spider silk has high tensile strength, allowing it to withstand large tension stress. It also has high ductility, allowing it to elongate under tensile stress without permanent damage. Spider silk is unique in that it carries both of these properties rather than sacrificing one for the other as is common in most materials. This toughness is a product of the silk's molecular structure. Dragline silk is a composite of 2 proteins. These proteins can be described as block copolymers with small polymer blocks consisting of 8 monomers. Each protein contains a non-crystalline matrix that gives elasticity to the silk, and each protein also contains a crystalline rigid matrix region that gives the silk toughness. The resulting structure is a polar hydrogen-bonded beta sheet. To give you an idea of the strength of spider silk, let's do a little thought experiment. How thick would a strand of spider silk need to be to stop a Boeing 747 flying at cruising speed? First, let's start with some initial values and assumptions. A fully loaded Boeing 747 carries a mass of around 430,000 kilograms and cruises at around 910 kilometers per hour. For the silk, we'll use dragline silk with a breaking stress of 1,550 million newtons per meter squared and 30% elongation at breaking. We'll assume this thread is weightless and that it follows Hooke's law. For these calculations, let's use a 500 meter long silk strand, which is roughly 7 times the length of the 747. Using an elongation of 30%, the silk will have 150 meters to stop the 747, an acceleration of negative 213 meters per second squared. First, we calculate the kinetic energy carried by the 747 using 1/2 mv squared, which comes out to be 1.38 times 10 to the 10th joules. The force required can then be calculated by dividing the energy by 1/2 the stopping distance of 150 meters, which comes out to be 1.8 times 10 to the 8th newtons. The surface area of the thread is then found by dividing this force by the breaking stress of dragline silk. The surface area required is 0.12 meters squared, which results in a 500 meter long strand of silk with a diameter of 40 centimeters being able to stop a fully loaded 747 flying at cruising speed. For comparison, 1090 mild steel would have to be 288 centimeters in diameter, assuming an elongation of 1%, and a hypothetical 500 meter long column of pure human skin would have to be 592 centimeters in diameter, assuming an elongation of 10%. The ability to synthesize and produce spider silk in a financially viable manner would revolutionize materials. That's why research is being conducted today to unlock and harness the secrets stored in the web.